This is going to be a brief introduction to the theory and practice of NMR, and after you watch this video, or you can even go look at it before you watch this video, there will be a quiz in Canvas for you to take that you should take before you come to lab this week. So NMR is a pretty important technique. NMR stands for nuclear magnetic resonance. One way that you can tell it's a really important technique is that it's won 4 Nobel Prizes, and I'll talk a little bit more about that in a second. As I've said in class, it's based on the interaction of electromagnetic radiation, specifically radio waves, with nuclei of atoms. And we'll see that hydrogen and carbon are the most common nuclei to look at, specifically the isotopes H1 and C13. But you can also look at phosphorus 32 and fluorine 19. Those are really common isotopes that are used. It's a little different from IR. IR is infrared radiation. It's a little bit higher energy. It's also, IR is a technique that can tell us what kind of functional groups we have in a molecule, whereas the 2 kinds of NMR we're going to look at can tell us about the carbon-hydrogen framework of a molecule, and you can imagine that's really important in organic chemistry. So I said I'd talk a little bit more about how NMR is a 4-time Nobel champion, and this just gives you a little bit of a history of the development of NMR. So it starts back in 1952, and that's when the Nobel Prize for Physics was awarded to Bloch and Purcell, and you can see it's for their development of new methods of nuclear magnetic precision measurements and discoveries in connection therewith. Big thing to notice about this is, yay, physics. I have joked a little bit about how physics is not our friend in terms of gravity and dropping highly breakable objects, but here is an example where physics is the friend to chemistry because they're the ones that discovered this technique, and it is incredibly important. Fast forward to 1991, and Richard Ernst won the Nobel Prize, and his Nobel Prize had to do with a lot of the techniques that we now use to help us understand the structure of molecules. So 1991's prize was the kind of stuff that related to the kind of stuff that we're going to be doing in lab, which is looking at small molecules and trying to determine the structure of them. In 2002, Wuthrich won the won the Nobel Prize for, he is starting to look at, or he won the Nobel Prize for looking at large structures. So this is the 3D structure of biological macromolecules in solution. So that's a big leap from looking at small molecules like, say, phenacetin or acetanilide or dichloromethane to looking at molecules like, say, the protein insulin or something like that. Finally, the most recent Nobel Prize was in medicine, and notice what it says here. It says for their discoveries concerning magnetic resonance imaging, or MRI. And most of you have either know someone or have actually had an MRI, and this is NMR. It's used to look at specifically hydrogen atoms that are in water that's in different bodily tissues, and depending on how they appear in the MRI, that can tell you something about the kind of tissue that it's in. And they had to take out the word, notice we went from nuclear magnetic resonance to magnetic resonance imaging, and they had to take the word nuclear out. You guys now know that nuclear has to do with just the nucleus of an atom, but people were worried because they associate the term nuclear with bombs. So when they put it into the medical field, they had to take out the nuclear part. Here's our friend, the electromagnetic spectrum. Week before last, we were talking about infrared spectra, and this week we are dealing with NMR, which deals with the radio waves portion of the spectrum. So it's much lower energy than infrared spectroscopy, and as I said, it's going to be interacting with the nucleus of the atom. And here's a quick aside. I bet you guys didn't realize you could create the entire visible spectrum from packets of condiments that one can find in pubs in the UK, but you can. Okay, back to NMR. Here gives you a sense of what NMR looks like in practice. Now, you have an NMR sample in a tube that you then place in a magnetic field. And what's going to happen then is you've got a radio frequency generator that is generating the radio frequency energy that's going to go into the sample. That sample then absorbs the energy at specific frequencies. It's then detected and goes to a display so that you can see it, very much like what we saw when you saw the infrared spectra. Here's an example of what the NMR looks like. This isn't actually our NMR. This is at Kurztown University, and they had a picture of one that looked. They have the same NMR we have, and I didn't have a picture. So here you go. Here's an NMR sample. As you can see, it's nice to have a hand there to give you a sense of scale. You have a small amount of sample in the bottom of a thin glass tube. Now that sample is going to be dissolved in deuterochloroform, or it might be a neat sample, which is just means that it's a pure sample with no solvent in it. So either way, you can do that. But the key thing is the sample must be liquid. We can't do, at least with our apparatus, we can't do the NMR of solids. And the NMR is pretty easy to operate, and we will be training you in the use of the NMR over the next couple of weeks. So what happens when you put your NMR sample into the magnet? Well, the first thing you need to know is you need to recall that all the nuclei in atoms are spinning at all times. And when charges spin, they're going to generate a small magnetic field. That's physics. And what happens is once you place the sample in the magnetic field, and this is just showing down here, is that we can either abbreviate magnetic field as H sub 0 or B sub 0. Those are both used in the literature commonly. But the key thing is, once you place them, those little nuclei in a magnetic field, they are going to line up with that magnetic field. Now, most of the nuclei are going to line up in a lower energy state, which is they're going to be aligned with the field. Some of the nuclei will line up in a higher energy state, meaning they're aligned against the magnetic field. And what we're looking at when we're looking at an absorbance or a peak in the NMR spectrum is we are looking at the difference in energy between a nucleus that is aligned with the magnetic field and it being spin flipped to where it's aligned against the magnetic field. So this slide gives you a sense of what happens when nuclei interact with electromagnetic radiation in the radio frequency region. So what happens here is, notice here on this axis we have energy, and on this axis we have the strength of the applied field. And point A is where you do not have the nuclei in a magnetic field. And so what happens is and therefore, there's no difference in any of the spins. But at point B and point C, what you can see is that at a higher strength of the magnetic field that the sample is in, there's going to be a larger difference in energy between a nuclei that is aligned with the magnetic field and a nuclei that is aligned against the magnetic field. And what happens is this process of a nuclei going from being aligned with the magnetic field to being aligned against the magnetic field is called a spin flip, and that occurs at characteristic frequencies of radio waves. And just like with infrared spectroscopy, those characteristic frequencies can tell us something about the molecule that's absorbing that energy. Now, the magnetic fields that are used in NMR can vary from 1.41 Tesla, which is often would be expressed as 60 megahertz, to 21 Tesla, which is expressed as 900 megahertz. Very, very high field instruments, basically going from about 300 megahertz and up. Those are superconducting magnets, and those magnets have to be cooled to liquid helium temperatures at all times. So they are pretty complicated and pretty expensive to maintain. Our NMR is a 90 megahertz NMR, and it's what's called a permanent magnet, meaning it's a magnet that is going to have its magnetic field. It may vary a little bit with temperature, but it's going to have a magnetic field no matter what temperature it's at. So it can hang out at room temperature and doesn't require us to have liquid nitrogen and liquid helium around it to cool to be magnetic. So that's very easy for us to maintain here at Guilford College. Now, physicists initially saw that when they tried to do NMR of more complicated molecules, that different nuclei, so different carbon or different hydrogen nuclei in the same molecule, experience different magnetic fields. So depending on what's around them, each of the nuclei, depending on whether, say, it's a primary carbon or a secondary carbon, or it's a carbon that's attached to bromine, or a hydrogen that's attached to a carbon that's attached to an oxygen. What that means is that those nuclei all are experiencing different magnetic fields. So you have the applied magnetic field, and then you have what's called a local magnetic field due to the surroundings, and that gives you what is essentially an effective magnetic field. Now, what that means is that different atoms can come into resonance or absorb radio frequency energy at different frequencies or different energies because of that. And so that means that, as we saw last week when we were looking at C13 NMR, one molecule may have several different absorbances or several different peaks at different places, and this is a H1 spectral window, which is about 10 parts per million. And when physicists saw this, what they decided to do is to call that, because it was due to the structure of the molecule, they decided to call it chemical shift. And different nuclei are referred to as being shielded or deshielded depending on their location, and that's going to affect where they absorb. So, for example, if a molecule or a specific nucleus is attached to something that is very electron withdrawing, like, say, a halogen or oxygen or something like that, what's going to happen is that is going to cause that atom to be what is referred to as deshielded, and therefore its absorbance will be shifted downfield, and that's what that. So downfield means away from, we'll call it zero. That's where TMS or tetramethylsilane absorbs. So downfield refers to higher ppm away from TMS. If a atom is surrounded by electron donating groups, or there are no electron withdrawing groups present, that is said to be shielded, and we find those absorbances upfield or closer to TMS. So the key thing here is that downfield refers to higher parts per million away from TMS at 0 parts per million, and upfield refers to absorbances at lower ppm or closer to TMS. And then you might be asking yourself, well, what in the world is this ppm thing? Well, ppm is the unit that we use to report absorbances in an NMR spectrum. And it's analogous to, we saw the reciprocal centimeter unit when we used to report the peaks that were the absorbances that we see in an infrared spectrum. And the reason that we use this is because this way we are able to report all NMR absorbances with a common unit, no matter how strong the magnet was of the NMR that the measurement was taken on. For example, if you were taking the proton spectrum or an H1 spectrum of deuterochloroform, there's only one kind of hydrogen in that molecule, so it only has one peak, but at 90 megahertz, that peak appears shifted 468 hertz downfield from TMS, whereas if you have a 500 megahertz NMR, then that peak is going to appear shifted 2600 hertz downfield from TMS. So we have two different chemical shifts here. So what we have to do is we have to normalize them. So we would divide each of those by the spectrometer frequency in megahertz, which would be 90 megahertz or 500 megahertz. And in both cases, that would give us 5.2 ppm. So we have the same chemical shift no matter what kind of NMR spectrum we take our spectrum on. Okay, a little bit about the differences between carbon-13 versus H1 NMR. As we mentioned in class, carbon-13 is not a very common isotope. It's only 1.1% of all carbon versus hydrogen, which is 99.9% of all hydrogen. Which means it's a little bit harder to acquire a C13 spectrum. It takes a longer time than it does to get a H1 spectrum, just because there's so few C13s. The other big difference is the spectral window. In C13, we're looking, as we saw in Chemactivity L3, we saw that we're looking at a window that is from 0 to 220 parts per million versus 0 to 10 parts per million. The chemical shift trends are similar in that as either hydrogens or carbons are close to electron withdrawing atoms like halogens or oxygen or nitrogen, then they are shifted downfield away from TMS. So that's the same also when atoms are involved in pi bonds or in pi bonds, then they also tend to be shifted downfield. In C13 NMR, you don't have any of what is called integration or splitting data. The signals are decoupled. Recall that in C13 we just see single peaks for each type of carbon that is present in the molecule. In H1 NMR, we use a technique called integration, which measures, recall from calculus that integration measures the area under a curve. So integration in H1 NMR, what that does is it measures the area under the peaks, and that's very useful because it can tell us the number of hydrogens associated with each peak. So that's a very valuable piece of information that we'll learn more about when we look more in depth at H1 NMR. So I mentioned that carbon-13, because it's not a very abundant isotope, that it takes a little bit longer for us to acquire a meaningful spectra. And here is a spectra for pentanol, 1-pentanol, and in 1-pentanol we have 5 different kinds of carbon, so we would expect to see 5 peaks in the C13 NMR. And you can see here that after one scan, Maybe we can see some of the peaks, but it's really hard because of all the noise. And so what we do instead is we would take 200 scans or more scans, and because the noise is random, it cancels out, and that allows us to see the actual peaks. Okay, because these peaks are thin lines, I went ahead and outlined them in blue so that you could see where they were and not get them confused with the graph marks there. And you can see we've got 5 different kinds of carbon. And while I can't assign every single one of them, I do know that this carbon is probably the one giving us that peak because it's attached to oxygen. So it is very electronegative, therefore it is shifted downfield away from zero, away from the TMS peak. The other peaks are all appearing in this area and are probably, but I don't know for sure, but they probably are, going closer to 0 ppm depending on how far away they are from that hydroxyl group. So that just gives you a little sense of what a C13 NMR is going to look like, and hopefully a brief overview that is useful of the theory and practice behind NMR. And finally, Dudley would like to remind you that it's very important that you stretch regularly so that you are limber when you are taking your NMR spectra.